Hello everybody. Today let's consider stress invariant. So before we talk about stress invariant, let's consider a vector first. Say we have a vector here. To represent this vector, so we need a coordinate system. So let's choose a coordinate system. So 1 and 2. So with this coordinate system, we represent this vector in the vector components using the coordinate system. But the same vector can be represented differently with respect to different choice of coordinate system. For example, if you choose 1 prime and 2 prime, here 1 prime and 2 prime, then we have another form of stress components. But make sure that we are talking about the same vector. So there is a quantity which is not changed with independent of the choice of coordinate system, which is the size of this vector, the magnitude. The size of this vector is not changed, so it is independent of the choice of coordinate system. This may be considered as an invariant to the stress, the vector. The same principle is applied to stress tensor here. So let's consider stress here. Say in the case of one-dimensional problem, we have one-dimensional stress. This is for 1D. But in the case of 3D, the stress is given by multiple stress component, sigma 1, 1, and 1, 2, 1, 3, and sigma 2, 1, sigma 2, 2, 2, 3, and sigma 3, 1, sigma 3, 2, and sigma 3, 3 here. So make sure that these 9 stress components can be considered as the vector components in this vector problem that we considered before. Then what would be the invariant? Is there any invariant in this stress tensor? Yes, there must be invariant too. In the case of this stress tensor, the invariant is determined as the first invariant. There are 3 different invariants. The first invariant is the sum of these diagonal terms, sigma 1, 1 and 2, 2 plus sigma 3, 3. And initial rotation, it can be given by sigma kk. So this repeating, k is repeating, which means sum over it. So k is repeating means sum over it. So which means that represents sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. The second invariant is the sum of subdeterminant. So the subdeterminant is here, and this is the second subdeterminant. And the third is subdeterminant with these 4 different components. Okay. So the subdeterminant is given by determinant of sigma 2, 2, 2, 3, sigma 3, 2, 3, 3 plus sigma 1, 1, 1, 3, sigma 3, 1, and sigma 3, 3. And then third subdeterminant is sigma 1, 1 and 1, 2, sigma 2, 1 and sigma 2, 2. Okay. So in initial form, it is also given by sigma I and sigma jj minus ij sigma ji. Okay. So make sure that this is also there are 2 repeating index, which means sum over I and j. So that is equal to sum over I and j. So which means sigma 1, 1, and then 1, 1. Okay, plus, and then this repeating index I and I, sigma 2, 1, and then sigma 1 and 2, blah 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 blah. Okay. And the third invariant is given by determinant of this stress tensor. This is a third invariant. Okay. So here the physical meaning, let's consider the physical meaning of the invariant. The first invariant represent, the sum, that is the sum over the diagonal term, which means the 3 times of hydrostatic pressure to the stress condition. So we can define the same invariant for stress deviator, which means here, so let's define a stress deviator, sigma ij is sigma ij minus the magnitude of a hydrostatic pressure, sigma v, Sigma v is a third of trace, sum over the diagonal terms. Maybe it can be given by I1 here, the first invariant, and then delta ij. So here delta ij means this is so 1 or 0. If I is equal to j, then it is equal to 1, or if it's not the same, this is equal to 0. And this is stress invariant. This is called deviatoric stress. Deviatoric stress. Then what's the physical meaning of deviatoric stress? The physical meaning of deviatoric stress is what we'd like to consider only the part of the stress which contribute to distortion of a material point. That's the physical meaning of the deviatoric stress. So we can define the same invariant here. So we can define in 3 invariant for this deviatoric stress. The 3 invariant defined for the deviatoric stress spatially we call J1 and J2 and J3, okay? Physically, but they are exactly same as the stress invariant that we discussed for the ordinary stress tensors here, okay? Because we consider only the deviatory stress part, that's why we use special the variable j, okay? So as you understand, J1 is equal to 0 because we already subtracted the hydrostatic components from the original stress tensor. So if you consider sum over the diagonal terms of this deviatoric stress, that should be equal to 0. Okay, so we can calculate the same for this deviatoric stress, and then we can calculate J2 and J3, blah blah. Okay. Then what is the relation between the so-called equivalent stress to some kind of stress invariant? So here, the equivalent stress, sometimes we call this is von Mises stress. This is given by square root of 3 of J2. What I mean, second invariant of deviatoric stress. Okay, that's the physical meaning of this. So you can represent this equivalent stress using the principal stress. So if you are able to calculate the principal stress, this is given by a half of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, that is the representation of equivalent stress. So what's going to happen if you don't have any the information for the principal stress? Then don't worry, we can do the same for same as in the ordinary stress terms. For example, this is given by a half of sigma 1 minus sigma 2 square by the definition. Okay, sigma 2 minus sigma 3 square, and then sigma 3 minus sigma 1 square plus 6 tau, not tau, what I mean, sigma 1 2 square, sigma 6 sigma 2 3 square, 6 sigma 3 1 square. Okay, so let's consider a special condition such as the plane stress condition. In the case of plane stress, sigma 3 is equal to 0, isn't it right? And then here sigma 3 is equal to 0, and also sigma 3 is equal to 0, sigma 3 is equal to 0. Or we can drop this the shear stress too. Okay, then we can easily obtain the expression of equivalent stress for the plane stress condition too. Okay, so let me stop here for the part of stress invariant, and then the relation is the relation to the equivalent stress.